Okay, guys, we'll continue our discussion about digital signal processing using Python. The topic is sampling, one of the important topics in signal processing. Okay, consider t equals to n times ts, where ts is the sampling time. A continuous time signal may be sampled into the discrete time signal if the Nyquist rate is considered. That is, Fs sampling frequency is equal to 1 over Ts, and it should be greater than or equal to 2 times Fmax, where Fmax is the maximum frequency of x of t. X of t is the input signal. Right. It can be done by multiplying the input signal with an impulse train. Figures 1.3 and 1.4 show the sampling in time and frequency domain respectively. So let's go through the figures because they carry very important information. Okay. A continuous time signal, say it x of t is what appearing in subplot 1, right? In blue color. We multiply x of t by impulse train. That's impulse train with similar distances. It is called TS, sampling time, TS, right? And looking back to shifting property, every sample will appear like this. So we'll pick the value of the amplitude of input signal, and the rest will be 0, and again another one, and another sample, and another sample, up to n. Sampling in time domain, right? Now, we'll continue the topic. A very important note. If only sampling occurs, then it's called the discrete time signal. Horizontally, it has been discretized. But what about the amplitude by itself? If the amplitude is quantized, then it will be a digital signal. So, please consider the difference between discrete time signal processing and digital signal processing. If a signal, a continuous time signal, is sampled by an impulse train, it will be called discrete time signal. And when we try to quantize the amplitude of the input signal, both horizontally and vertically, the achievement is done. So it will be later called digital signal and digital signal processing. Of course, the quantization will be explained later. It is clear that if omega s less than omega 0, then the spectral overlap will happen, and it's called aliasing, spectral overlap. Again, repeating, aliasing, spectral overlap. It is said that in this case, the Nyquist rate has not been met. We'll show later how spectral overlap and aliasing will happen by illustration, very clear illustration. Right. After sampling, we'll have some very useful and important information in frequency domain. Here in this figure, we consider frequency domain information. Suppose input signal has a band limited is a band limited signal and has values up to omega max. The best shape to illustrate such an idea is what you see here. Okay, we know that the frequency information for impulse train is again impulse train in frequency domain. So impulse train in time domain will lead to impulse train in frequency domain, of course, with the relevant frequencies. Okay? Now, we remember that multiplication in time domain will lead to convolution in frequency domain. So that's the result. Every impulse will carry the input frequency response. You see here? That one carrying it, and the next one, and it's a kind of mounting, and so. Okay. And the caption is, of course, sampling of a cosine signal with a sampling frequency of fs. Here, let's go back to, everything has been explained here. Now, we consider an example, sampling of a cosine signal with a sampling frequency of fs, sampling frequency. X of t is a cosine, omega 0 t, and of course another explanation, cosine of 2 times p times f0 times t. If we replace t with n times ts, we'll reach to such equation. Omega 0 n. Omega 0 n times ts, 2 times p times f0 times n times ts. Where here you see the definition of omega 0 and how it's related to capital omega 0. Okay? So, write down this information. Here we note another problem. The dimension of omega 0 is radian per second, but its dimension is radian. Or to say it clearly, radian per sample times sample. In any case, it's radian. Okay? Now, we are trying to write our first program in Python environment. So, write a simple Python program to read an audio file. Here you see the details, a simple program to read an audio file. We use some import declared here. Just to save the time, I won't explain them. Just running the program. Okay? Fast scrolling of the codes. Right? To reach the end. I'll try to attach the file somewhere in YouTube. I haven't tried it yet. Okay, just plotting the information. Now, I will try it in inside pie chart. The same information here. Just scrolling from top to bottom. The same information. Okay. Now I'll run it. Okay. Figure 1, you see the figure 1? Plot our audio signal left channel. Did you see here the duration of the signal? Something somehow greater than 2 seconds. The second figure, here is right channel. And the third one, plotting 2 channels besides. Okay.